In this video, we're going to cover section 2.1.2, which in particular includes the derivation of the equations of a line in R3. So in the last video, we had seen that your familiar general form equation of a line from high school does not yield a line in R3, it yields a plane. And so that begs the question, what does yield the equation of a line? And the problem that we're going to have is that the concept of slope is not well defined in three-dimensional space. And so we are going to need to rethink the geometry of the line using something that does generalize well to three dimension, and that something is going to be vectors. So remember that we used two things to give the equation of a line in R2. We used the slope of the line and we used a point on the line. And it turns out that we can replace both of these things with vectors. So let's look at our diagram here. So if we had 2 points on the line, right, we had x1, y1, x2, y2, we can create a vector d going between them. And if we let d v delta x delta y, then d is capturing exactly the same information as the slope. And also, I mean, d can be drawn anywhere, but wherever d is drawn, d is going to be parallel to the line. So slope can be replaced by this vector d. We will still need a point on the line, right? A point, let's say x1, y1, could be x2, y2, could be the y-intercept, doesn't matter. And we can take this point and express it in terms of its position vector as well. So now we're replacing both things that we need for the line with vectors. So let's take that idea and go forward into three-dimensional space. So let's do the following, the derivation of the equation of a line in R3. So let L be a line in R3, and let's say we're given a point P, x0, y0, z0 on L, and a vector D. D, which incidentally is usually called the direction. That's why it's called D, the direction vector. And this vector needs to be parallel to L. We are going to derive the vector equation for L. We're going to derive the parametric equations for L and the symmetric equations for L. So let's start by adding a little something here. We're going to let point Q, x, y, z be any other point. So any point on L. So let me go ahead and draw point Q, let's say here. So there's our point Q. Here's its position vector OQ. And that gives us a vector between these 2 points here. So let's call this the vector PQ. And so what do we notice? Well, first of all, this vector PQ has to be parallel to the given vector D. And if vectors are parallel, you saw in the last chapter that they have to be scalar multiples. So we're going to use T for some T in R. That's the traditional scalar that we use for lines. So PQ has to be some multiple T of D. Now, PQ, we've got a lovely tip-to-tail relationship between the vectors there. So we have PQ is OQ minus OP has to be T times D. And if we solve for the unknown point, any point OQ, or the position of OQ, in terms of the given information, we have this, which tells us that x, y, z is equal to x0, y0, z0 plus t times d1, d2, d3 for some t in R. Okay, and this actually is the vector form equation of our line. This is the vector form equation of our line L. So let's go back and go and interpret. Let's interpret some of these things geometrically. Let's remind ourselves of what they are. So this x, y, z, that is our vector OQ. That's the position vector of any point Q. of any q, x, y, z, which is on the line. This vector here, that was the position OP. That's the position vector of the known point, right? Because P was given. And then we have this vector here, D, our direction vector. D is any vector that is parallel to our line. So there's one thing that we're missing here in terms of a geometric interpretation. There's one thing that we're missing here, and that is, what does T represent? What does T represent? Well, we look here. This is the same T up here. It's the number of multiples PQ is of D. So if I look at my drawing, right, let's say 1, 2, 3 maybe, right? 3 times this, well, in the opposite direction. So my T is approximately -3. So T is the number of multiples of the direction vector that you need to get from your point P to any unknown point Q, right? And if you change T to anything you want, you can get to any other point on the line. And so that's what this little remark here is telling us. Right, we can describe the position vector of every point on L, right? Every point, Q was any point that we wanted, as the sum of the position vector of a known point and a scalar multiple of the direction vector. All right, good. So let's go ahead and do the parametric equations for L. Now that's really simple here. All we're going to do is read component by component through the vector equation. So if I read the x component, then x in the first component is x0 plus t times d1. Simple. I read the y component. So y is the second component, y0 plus t times d2. And I read the third component for z. Z is z0 plus t times d3. That, of course, is for some t in R, and that is the set of parametric equations for L. That's it. Now, we'll notice that each and every one of those equations has t in it. And if we go ahead and solve for t in each of those things and set them all equal, we can get what is called the symmetric form equations, right? So if I take t and I solve for t in the first equation, I'm going to get x minus x0 over d1. And in the second equation, t is going to be equal to y minus y0 over d2. Now, since they're equal to the same t, those things are equal to each other. And the last equation, z minus z0 over d3. And this t actually, I mean, this is all equal to t, but we don't write that. What we write for the symmetric form equations is this. Now, of course, that needs d1, d2, and d3 to be non-zero. And so what happens with a case that one of them is zero? Well, we're going to do an example in the next video, and we'll see how we write the symmetric form equations when one of those is zero.